In this video, we'll talk about how we can prove a function is surjective. So let's first remember the definition, which says that a function f from s to t is surjective, or onto, if for all lowercase t in capital T, so these are elements in the codomain, for all of them, there needs to exist an element lowercase s in the domain such that f of lowercase s needs to be equal to t. So there has to be some input that gets me that output. That needs to be true for all of the outputs in the codomain. So another way of saying that is that everything in the codomain gets what I call landed on. Landed on. There's something in the domain that will, when I plug it in, will get me to that thing in the codomain. So to prove a function is surjective, my structure is I let lowercase t be an arbitrary element of the codomain. And then what I want to do is show there exists an element s in the domain such that f of s will be equal to t. So if I can do this for an arbitrary element in the codomain, well, that means it's going to be true no matter which element in the codomain we pick. On the other hand, if I want to prove something is not surjective, well, I got to show that I got to find just even one value in the codomain such that no matter which element I pick in the domain, that f of s, no matter which input I plug in, f of s will not be equal to t. Okay. So let's do an example. Let us do an example. Let's say that f is a function from R to R. So the domain is the reals, the codomain is the reals, and f of x is negative 2x plus 5. First, I want to show this is surjective graphically. So if I draw some axes, and then I draw the graph, this is a slope of negative 2, and the y-intercept is positive 5. So something like this. Well, it's surjective if everything in the codomain, in this case, every y value, every real y value gets achieved. Well, that's clearly true. No matter which y value I pick, like this one, there's a point on the graph where I reach it. Or this y value, there's a point on the graph where I reach it. Or this y value, there's a point on the graph where I reach it. So the fact that I can do that no matter which real I pick in the codomain means it is surjective. So this thing is surjective, because every real y value is achieved. And we see that graphically. Now in part B, let's actually prove this thing is surjective using our definition of surjectivity. So we're going to use this structure. So I'm going to start this off with scratch work. So what is the stuff that I'm given, / the things that I get to assume are true? So we get to let t be an arbitrary element of my codomain, which in this case is R. And then what I want to show is, I'll put a bullet point here, that there exists some element lowercase s in my domain, which in this case is the reals, such that when I plug that into my function, f of s will be equal to t. So no matter which t I pick, I'm going to have to be arbitrary. I'll be able to find an input that gets me to that output. Okay, so typically I would work with the things that I'm given, try to do stuff with it until I can get to what I want to show. But in this problem, I don't have much to go off of in terms of what I'm given. I just know that t is reals. So instead, I'm going to work with what it is that I want to show and see if I can sort of work backwards. So if f of s is t, what that means, that's equivalent to saying f of s, if I plug into my function, would be saying that negative 2s plus 5 equals t. So what I can do is I can just solve this equation to figure out what the s is that I'll need to pick. So if I subtract 5, I get negative 2s equals t minus 5. And then I divide the negative 2 to get s equals t minus 5, that whole thing divided by negative 2. So it seems like if I pick s to be this value, and if I plug it into the function, hopefully the output should be equal to t, because that's what's happening when I try to solve for it. Okay, so I think I'm ready for the proof. So in the proof, I get to start off by writing down all the things that I know are true, or I get to assume are true, which in this case is I let t be a real number. This is an arbitrary value in my codomain. Okay, now the scratch work has helped me determine, well, what should I pick for the input? So I'm going to assert that. Let's pick this input s to be t minus 5 over negative 2. And I notice that, well, I'm just subtracting and dividing numbers. I'm not dividing by 0 or anything. So this is very much a real number. So this is a real number, meaning it's in the domain. So now let's show that if we plug it in to the function, that I get t as an output. So let's do some manipulations. So let's do f of s. Let's use some words here. Then if I compute f of s, what we get is negative 2 times s, t minus 5 over negative 2, and then plus that other 5 out there. Let's simplify this. So the negative 2's cancel, and I get t minus 5 plus 5. The 5's cancel, and I get t. But that's precisely what I wanted to show. So sometimes when I get that, I like to write a couple of words like as desired. That is exactly what I wanted to get. That's what that means. So therefore, this function f is indeed surjective. And that's my proof. So let's review the structure again. To show something is surjective, I start off by picking an arbitrary element that's in the codomain. In this case, that was the reals. And then what I want to show is I want to find some element in the domain. So often I'll have to figure out what that is by doing some scratch work like I did here, and show that when you plug it into your function, and you simplify it, you'll end up getting t as the output. And that shows that no matter which t we pick in the codomain, we're able to find some input that gets me to that output. And that's what it means to be surjective.